All right. Sequences and series, section 9.1. We're going to start out by finding certain sequences and certain series, and these have terms to them, and they're usually written terms in this form. So the first term would be a sub 1, for example. So we use integers here, right? A sub 2 would be the second term, a sub 3, a sub 4, and so on. And sometimes you might have an infinite sequence where the terms will never end. And sometimes you might have a finite sequence where, it might only have 5 terms or 10 terms or something like that. Okay? So it'll be a sub some positive integer, usually. And it can keep going, of course, if it's infinite. Let's start off with a couple easy ones. Example 1. We're going to find, this is part A. Find the first 4 terms of the sequence given by. So find first 4 terms of this sequence. So the sequence is given by a sub n equals 3n minus 2. So since we want 4 terms, that means we're going to find a1, a2, a3, and a4. Okay, and the model up there is what we use to find each term. So if I want a1, that means that n is 1, so that's going to be 3 times 1 minus 2. This will be 3 times 2 minus 2, 3 times 3 minus 2, and 3 times 4 minus 2. First term will be 3 minus 2, then 6 minus 2, 9 minus 2, and 12 minus 2. So our 4 terms for this sequence are 1, 4, 7, and 10. Part B, same thing, but different formula for each term. A sub n will be given by 3 plus negative 1 to the n power. They also want the first 4 terms. A1, 2, 3, and 4. So we have 3 plus negative 1 to the 1 power, right? When n is 1 for this one. And then 3 plus negative 1 to the n is 2 for this one. And then n is 3. And n is 4. Negative 1 to the 1 will be negative 1, so negative 1 and 3 in this case will just give us 2. Then negative 1 squared is positive 1 plus 3 will give us 4. Negative 1 cubed will be a negative 1 plus 3 is 2. And negative 1 to an even power will be a positive 1 plus 3 is 4. And you start to see the pattern, right? If they would ask us to write 20 more terms, for example, we can see that it's just going to switch off between the 2 and the 4. Okay? Any questions on these two? So we just were asked to find the first 4 terms of 2 different sequences. Example 2, Let's try one with a fractional expression. Same idea, we're still going to find the first four terms. Expression will be a sub n is equal to -1 to the n power over 2 times n plus 1. So this one not only has a fraction but also has n twice, right? In the exponent and also in the denominator. So we'll do a sub 1. We would have -1 to the 1 power over 2 times 1 plus 1. A sub 2 would be -1 to the second power over 2 times 2 plus 1. So here we have -1 over 2 times 1 is 2 plus 1, so we have 3. And for the second term, we have -1 squared, so that's going to be +1 over 4 plus 1, 1/5. A sub 3, -1 to the third power over 2 times 3 plus 1. This will be -1 over 6 plus 1. And then the fourth term will give us a +1 on top and a 2 times 4 plus 1 on the bottom. So we got +1 over 9. And you can see how these this sequence will have the terms, they'll keep alternating in sign, right? We have a negative term to start, then the positive term, then the negative term, then the positive term, and so on. We can also go, well, we should also be able to go backwards. So given the terms, can we come up with the nth term expression, right? Nth term formula for a sequence. Example 3, part A. For the nth term. The sequence for A is 1, 3, 5, 7. So we can come up with any model that'll fit these first four terms, and that we can use to find more terms if we need to. In this case, because they're just the odd numbers starting with 1. If you think about it, the way we write the even numbers is just 2 times an integer, right? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on. So we can think of this nth expression as 2 to the n would give us all the, remember we're thinking about starting with n equals 1. 2 to the n would give us the even numbers. And then if we want to get the odd numbers, we would just subtract 1, right? So we want one lower than the even numbers. So that would be 2n minus 1. And double check it, right? So plug in 1, 2 times 1 minus 1, 2 times 2 minus 1, 3, 2 times 3 minus 1, and 2 times 4 minus 1, and so on. B, same idea, but the expression is, or I should say the terms are 2. Negative 5, 10, negative 17. Okay. We got to get 2, negative 5 for the second term, positive 10 for the third term, and negative 17 for the fourth term. If you notice, the signs are flipping, right, from one term to the next. Positive, negative, positive, negative. So that means for sure we're going to have some sort of negative 1 to a power as part of this. And to what power? If I do n power, then the first term would be negative 1 to the 1. That would give me a negative number, right? Negative 1 to the 1 is negative 1. But this is positive, right? So I need this to be positive in the first term. So that would be negative 1 to the n plus 1. N plus 1. Let's check if that gives us the right signs, right? So for the first term, that would be plug in a 1. So that's negative 1 squared, positive. So the second term, that would be a 2. Negative 1 to the third power is negative. And then negative 1 to the fourth power is positive. And then 1 to the fifth power is negative. So that part takes care of the signs, right? What about the magnitudes? 2, 5, 10, 17. How can we get that? So for the first one, I need to get a 2 when I plug in a 1, right? I need to get a 2 when I plug in a 1. So you might try different things. Might not always work. But let's just say I started with something like this, right? A 2 when I plug in a 1. So n is 1. So don't worry about the plus and minus, right? The 6 are that. So just worry about getting a 2, 5, 10, 17. Plugging the 1 here, right? 2 times 1 is 2, so it works for this one. But then you check the next one, this would be what, 2? So 2 times 2 is not 5, right? So we know that this can't be 2n. So what else can we do? Or can we try? Uh, 2n doesn't work. 2n plus 1 will give us a 5 for the second term, but it wouldn't give us a 2 for the first term. So 2n plus 1 also would not work. What about exponents, right? What about a power? N squared? If I do n squared, plug in a 1, that would be 1 squared, right? 1. 2 squared would be 4. 9, 16. Well, 1, 4, 9, 16, they're all 1 away. So I can just do n squared plus 1. Just write it like that. And so yeah, plug in the 1, that's 1 squared plus 1, so we get 2. 2 squared plus 1, so that's 4 plus 1, gives you 5. 3 squared plus 1, 9 plus 1 gives you 10, and 4 squared, 16 plus 1 gives you 17. Good. There's also the idea of what they call a recursive sequence. So some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms, and all other terms of the sequence are then defined using previous terms. For example, so in this recursive sequence, let's say they give you A1 is 3, and they say A sub k, this term is given by 2 times A sub k minus 1 plus 1. And in this case, k is greater than or equal to 2. And then they would tell you, find the first 5 terms or however many terms they want. In this case, let's do 5. So we know the first term already because they gave it to us. We know the first term is 3, right? A sub 1 is 3. So now we need A2. And what they give us is this recursive formula here. So A sub 2 is what we're looking for. Can k be 2? It says here that k can be greater than or equal to 2. So it is allowed to be 2, right? So we can plug in 2 here. So let's let k be 2, which means that A sub 2 will be equal to 2 times A sub 2 minus 1 plus 1. This is the same as 2 times A sub 1 plus 1. And notice here, we need this previous term. We're looking for A sub 2, but we need A sub 1 to find it, right? So that's why they gave us this in the beginning. That's 3. 2 times 3 plus 1. So the first term is 3, second term is 7. And then we do the same thing to find the rest. A sub 3. If k is 3, that means we'll have 2 times A sub 3. Oops, I meant to put a 3 there. Minus 1. Plus 1. So this is 2 times A sub 2 plus 1. In this one, we require the second term. And the second term, we just found it here, right? So we know that's 7. (14 plus 1) gives us 15. Fourth term, k is 4, so this is A k minus 1. It's 4 minus 1 plus 1. This is the third term times 2 plus 1. Third term, we got 15. So this is 30 plus 1. And then the last term, k is 5. So we got 2 times A4 plus 1. A4 was 31 times 2 is 62 plus 1 is 63. So that's what they mean by cursive sequence. They'll give you, in this case, they give us the first term, and then formula for finding terms A sub 2 and forward, right? Now, before we get into summation notations of sums, we need to know what a factorial is. So n has to be a positive integer. So like 1, 2, 3, 4, 5, 6, 7, etc. So never a decimal and never negative. The factorial symbol is when you see n with an exclamation point or a number with an exclamation point. And it means 1 times 2 times 3 times 4 all the way up to whatever n is. Right, so if, for example, 5 factorial would be 1 times 2 times 3 times 4 times 5. Mosquito here. And you would multiply those out to get the value. In this case, this is what 20. 5 times 4 is 20, times 3 is 60, times 2 is 120. And there's a special case of 0 factorial that's always equal to 1. Okay? 1 factorial would also be equal to 1. All right, first 3 terms of this sequence, they want us to start with n is equal to 0. So we'll do a sub 0 first, and then a1 and a2. So 0 means we plug in the 0 for n. So we got 2 to the 0 over 0 factorial. So anything to the 0 power, of course, is 1. And 0 factorial now we know is 1. So a sub 0 is 1. This will be our first term. A sub 1, got 2 to the 1 over 1 factorial. 2 to the 1 is 2, and 1 factorial is also 1. So we get 2 divided by 1. And the third one, a sub 2. This is 2 squared over 2 factorial. So 2 squared is, of course, 4. And 2 factorial would be 1 times 2. So we just get 2 there. And this is also equal to 2. Now, because they're including factorial expressions now into some of these, let's see how we simplify some of these that might have more than 1 factorial in them, some of these expressions. So here we're just going to simplify, for example, 7. Simplify 8 factorial over 2 factorial times 6 factorial. So be careful, these are not, they don't follow the same rules usually. For example, 8 factorial and 2 factorial are not divisible. Not automatically, right? You have to think of them as an expanded term. So let's do this a long way first. 8 factorial would be all 1 times 2 times 3 all the way up to 8, right? 4, 5, 6, 7, 8, like that. 2 factorial would be 1 times 2. And then 6 factorial would be 1 times 2 times 3 times 4 times 5 times 6. And now seeing them in this expanded form, we can see what factors they have in common, right? Then we can cancel stuff out. So if you notice, we have the factors 1 through 6 for sure on both the top and the bottom. So that will divide out with that to get 1. And we'll be left with 7 times 8 on the top and 1 times 2 on the bottom. But because I know 1 times 2 is just 2, I could also divide that into the 8, for example, right? And that would be a 4 now. So really I'm left with now a 1 in the denominator, so I don't have to worry about the denominator anymore. And on top, just 7 times 4. So this would simplify to just 28. We can also think about factorials in general terms in order to simplify. So if we were given n factorial over n minus 1 factorial, we know that whatever n is, right, we're going to multiply from 1 all the way up to n. So it looks something like this. All the way up to n, but if you think about it, if n is where you stop, what is right before n? Right before n would be n minus 1, and then you add 1 more to get to n, right? N would be the last one in that product. Over n minus 1 factorial, so this is going to go from 1 all the way to n minus 1. It'll actually be, before we get to n minus 1, it'll actually be n minus 2, and then we'll get to n minus 1, right? And that's the last term, since it was n minus 1 factorial. And of course, you can see that the top and bottom, we have all the terms up to n minus 1, right? So all this will cancel with all of that. Yeah, we'll be left with n over 1, so we'll just n at the end here. Let me add another one here. Kind of more simple, but tends to confuse a lot of people. Something like this. Sometimes tricks a lot of people, right? 16 and 8 looks very divisible. So don't be fooled into thinking it's 2, and don't be fooled into thinking it's 2 factorial. It's neither one of those. So think about it, right? This is going to go from 1 all the way to 16, and this will go from 1 all the way to 8. So if I think about it like this, I can say, okay, well, this is 16 times 15 times 14 times 13, 12, 11, 10, 9, 8, and then from 8 it keeps going down, right? So I'm going to stop here and just put a factorial sign because I know I have an 8 factorial on the bottom. So I know for sure that 8 factorial will cancel out with 8 factorial because they are the same value. Like that, right? And then at that point, you're left with just this product. So we would have to do repeat this out. 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9. All right, summation notation. So that was more background so we can work with these easier moving forward. Those types of processes, right? Like doing factorial, etc. Summation notation. So this is where we have sigma, and it represents the sum of the first n terms in a sequence. So it looks like this. And usually you have some sort of index here in the bottom, such as I equals 1. And then on the top, it'll have like where you end at, right? So you start with 1, and then you go all the way up to whatever n is. So it could be 50 or 100 or something like that. And then you have some expression here. Let's call it a sub I for now. It's just the general form of it. And basically what it means is find all the terms of this sequence, but we're going to sum them up together, right? So that's what the sigma means. So you would find A1, A2, A3, and notice we're adding here all these, not just writing them out with a comma, right? And this goes all the way up to A sub n, right? And n, of course, is the value up here on top of the sigma. So that's how we'll know where to stop. So example A, part A, let's say they want us to find this summation. So this sum goes from I1 all the way up to 5, n of 5, and our expression will be 3 times the index, right? 3 times I. So we'll find the first one, A1 in this case would be 3 times 1, plus the next one, 3 times 2, plus A3 will be 3 times 3, A4, and this will be A5. And then we just calculate it out, right? So we have 3 plus 6 plus 9 plus 12 plus 15. This should give us 45. When you add it all up. So notice how these went from, this had 5 terms in it, right? Because the index went from 1 to 5. So we have 1 term for each index value. B, this sum is from k equals 3 all the way to n is 6. expression is 1 plus k squared. So this one's starting off with an index of 3. So this is what goes in here first. And we're going to do 3, we're going to do 4, 5, and 6. So we're going to have 4 terms, right? 3, 4, 5, and 6 is 4 terms. So we have the first term plus the second term plus the third term. K is 5 for that one. And the fourth term. So for this one, K was 3, K was 4, K was 5, and K was 6. And then you calculate these out. This is 10 plus 17 plus 26 plus 37. So for this one, we get 90. Any questions on those first two? What? Oh, so with it. I don't think this really has alcohol because it doesn't really do anything to it. I've already gotten it like 3 times. Part C, another sum. Index is 0 and it goes all the way up to 8. So for this one, we'll actually start with an I of 0. And then we'll plug in 1, 2, 3, 4, 5, 6, 7, and 8. So we'll have a total of 9 terms for this one. And notice there's a factorial symbol in it for the denominator. So the first one would be 1 over 0 factorial. And because it's sigma, it's always going to be plus the next term. 1 over 1 factorial. 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial all the way to 8. So each one of those factorials, you would calculate it out. Your calculator should have most of them have a factorial button somewhere. You'll see a little exclamation point somewhere in there. So use that. It'll be much easier than doing it one at a time, like 8 times 7 times 6 times 5, etc. And calculate out the denominators. So the first one is just 1 over 1, and the second one is also just 1 over 1. Then we have 1 over 2 factorial, 1 over 3 factorial is 1 over 6, 1 over 4 factorial, 4 factorial is 24, 5 factorial is 120, we did that one earlier, 6 factorial is 720, 7 factorial is 5040, and 8 factorial is 40,320. So adding all these, all this up, we'll get an approximation, a decimal approximation here of 2.71828. I shouldn't put the exclamation mark since we're talking about factorial. So this is the value of E, right? Euler's number E. Should we remember from, especially from pre-cal 1, right? The natural log and all that. So this is how you actually get that value. Except you wouldn't just do 9 terms, right? For E, it keeps going on forever. So that's why it's an irrational number. But this is how they get that Euler's number E. It's very, very close to the actual value. So these sums so far have been pretty straightforward, right? Nothing too complicated in order to find all the different terms. But what are some properties of sums that we can use when they do get a little more complicated, a little more involved? Well, first property, if you are given a sum from 1 to n of a constant, so like instead of writing an expression here, you just write like 5 or something like that, where you can't plug anything in, it will be equal to the constant times whatever your n value is. So you can just convert it directly into a value, c times n. Also, if you're given a sum from 1 to n, and you have a constant in here that you can factor out of an expression, so the expression will be a sub I, right? That's what the little formula they give you to plug in the i's. You can actually factor out take out the constant in front of it. To simplify this a bit, so I can take the constant out in front of the sum, and I can just do this for the expression AI. So I would still do the whole process, right, from 1 to n, but I can take this constant out. So let's say this constant was like 5,000. I don't have to leave it in here. I can take it out, do that first, and then at the end multiply by 5,000. So we can factor out constants. If you have a sum with two expressions, a sum of two expressions, so we have a formula a sub I, and then a second one that we can separate as a sum of two things, like this. I can actually break this up into two different sigmas. So we can actually write this as 1 sigma plus another sigma. And remember, you can use these backwards as well, right? So if you have two sigmas like this broken up, you can rewrite it as 1 as well. And the fourth property they have is same as 3, but for subtraction. one sigma minus another. So we started off finding the terms of a sequence, and then we moved into summations, right? So adding up the terms of a sequence. So when we add sums of the terms of a finite or infinite sequence, we can call this sum a series. Example 9. The series here is going to be there's two parts to this, so let's do one at a time. So for A, they want what they call the third partial sum. So let's write that out. Find the third partial sum. This is sigma from 1, and they said it could be finite or infinite, so this is infinite. 3 10 to the I, 3 over 10 to the I power. That's what it is. Now for, we'll get to the infinity part in the second part here, but for this one, they just want the third partial sum, so all they want is the first 3 terms. So instead of going to infinity, we'll go from 1 to 3 for this one. We'll go from 1 to 3. And it works just like the other ones, right? Plug in the 1, plug in the 2, and then plug in the 3. So we got 3 over 10 to the 1, plus 3 over 10 to the 2, plus 3 over 10 cubed. This is 3/10 over 3 over 100 over 3 over 1,000. If we think of these as decimals, oops, looks something like that, right? .333. So that's what they mean by partial sum. But let's actually find the sum now, as it was given. From 1 to infinity of 3 over 10 to the I power. Now, because we already saw what the first 3 look like, right? So think about it. If I do the 4th, 5th, 6th, 7th, 10th term, what's going to happen? 0.3, 0.03, 0.003, 0.0003, right? It's going to keep going like that. So what are we going to end up with? 333 forever, right? And what's another way of saying that in a fraction form? What is 0.333333 forever in fraction form? 1 1 over 3. And that would be the exact value. Okay. All right, 9.2